Venus. At the surface, its air is 95% carbon dioxide. The atmospheric pressure is like being 900 meters deep in Earth's oceans. It's hotter than anywhere else in the solar system except the Sun. And yet, visionary engineers and scientists are now unveiling daring new strategies to explore its tortured landscapes, to sail its turbulent upper-level winds, to imagine altering its very climate. They are taking the first steps toward settling the second planet from the Sun.
Ignition sequence started. All engines are started. We have a liftoff. We have a liftoff, and it's lighting up the area.
The early 1970s. The space age was at its peak. The Apollo astronauts were exploring the moon.
Those rocks would wait 4.5 billion years for us to come grab them.
Robotic spacecraft had visited Venus, Mars, Mercury, and Jupiter, with new missions on the drawing boards. And yet, in those heady days, America and Europe faced a series of daunting challenges. The ongoing Cold War, unchecked industrial pollution, race and class conflict, a sudden fuel shortage. Many thought that only strict Earth preservation and laws limiting industry could save civilization. Meanwhile, a small cadre of scientists, philosophers, and writers sought answers in far-sighted engineering. Decentralized information systems, which later became the Internet and cellular networks. Molecular biology, which led to gene sequencing and the promise of nanotechnology. And human expansion into space. They envisioned moon bases, cities on Mars, grand orbital habitats. The so-called space colonies would pioneer a whole new way of living. Future residents in space would be free to live by whatever social contracts they chose. Huge structures, assembled by astronauts and robots, they would draw upon resources on the moon.
Stand by for pitch over. Thor, we coming in.
Materials from asteroids, and on the free energy of the sun. These plans consistently overlooked one planet, Venus. Hellishly hot and enveloped in a crushing atmosphere. How could anyone ever live there? To some visionary thinkers, Venus held a unique promise, one that led to one of the most innovative mission ideas on the books. A spacecraft carrying astronauts is bound inward toward the Sun. It slips into low orbit around Venus, docking with an uncrewed sister ship sent months before. One will deorbit, protected by an aeroshell as it bleeds speed into heat. A parachute further slows the vehicle. But it isn't heading for a landing. Instead of continuing to the surface, it deploys an inflating envelope, an airship up to 130 meters in length. The high-altitude Venus operational concept, Havoc. Its crew sails for about 30 Earth days, navigating in the fast winds, suspended beneath an inflated envelope of helium gas. Circling the planet, they deploy probes to learn about its atmosphere and geology. They send out a fleet of small robotic balloons to dip down into the hostile lower atmosphere. Their studies complete, the crew ascends to their transport ship in orbit. Then, kicked off by a powerful rocket, they escape Venus's nearly Earth-level gravity and make the 100-day journey back to Earth. Havoc-style missions would set the stage for a long-term plan to permanently settle Venus. Though the landscape of Venus is a hot, high-pressure death trap, the upper atmosphere could offer safe harbor.
In the clouds of Venus, which is 50 kilometers up from the surface, there is a realm where it's very much Earth-like in terms of the conditions, except for the clouds themselves are made out of concentrated sulfuric acid.
Of course, you still have no atmosphere with oxygen in it. You still have the sulfur oxides that give you sulfuric acid, so you don't want to go outside without any protection. But in terms of temperature and pressure, it's very, very Earth-like.
So you can imagine sending humans there in some kind of a balloon platform or some other floating platform to explore the clouds of Venus, and you wouldn't need a pressure suit, and you wouldn't have to worry about the thermal environment. It would be quite pleasant. You would just need some thin protection from the acid clouds, and you would need a breathing apparatus since it's mostly carbon dioxide. But in terms of the environment, say compared to the surface of Mars, the clouds of Venus would be a much easier place to send human beings.
Let's take a slice of the planet's atmosphere, from the sweltering ground to the vacuum of space, 200 kilometers tall. On the surface, you'd feel as squeezed as diving nearly a kilometer underwater and being baked twice as hot as in a pizza oven. But rise up 50 kilometers and you'll enjoy Earth normal pressure and springtime temperatures. This moderate zone, high in the atmosphere, has plenty of light, but not too much radiation. It's an ideal location for a research station. Imagine frequent flights into the stormy clouds of Venus. The airships would be spun from carbon fiber, harvested from the atmosphere itself. Their electric motors powered by the sun. Ahead, a permanent floating station. A cloud city awaits.
I have been thinking of this idea that you could float habitats in the atmosphere of Venus. And the habitats could be very large. They could be kilometers in scale. And the interesting thing is, if you did this, you wouldn't even need to have hydrogen or helium to make them float, because the atmosphere of Venus is mostly carbon dioxide. Oxygen and nitrogen, ordinary breathable air, would float in the atmosphere of Venus. And inside, there are giant bubbles. You can walk around on the inside, because the air that's holding you up is also the air that you can breathe. The lifting gas is your environment.
The interior ecosystem can be lush, with plenty of room to breathe and plenty of acreage for growing food. This home in the clouds can be nearly self-sustaining. Looking up through the transparent domed rooftop, you watch vessels come and go. Suspended beneath the habitat, the logistics hub, to house its core services and computer systems. The docking ports are staggered across 2 levels to accommodate the wide girths of several airships at once. Expeditions set off, launching instruments as they go. They'll diverge onto different courses, running survey transects above the surface of Venus.
There are some experiments that you could only do if you actually go and float around in the atmosphere. And what you could do is answer a lot of the mysteries that remain about the atmosphere and the clouds. There's a lot we don't know about what the clouds are made out of, what kind of chemistry is going on there. There are gases we call the rare gases, neon, argon, krypton, xenon, or the noble gases. And they're called the noble gases because they don't react with other gases. They're on the periodic table. They're the column all the way on the right. And they don't react with anything. And because of that, they tend to record long-term aspects of a planet's history, because they haven't sort of been perturbed by chemistry. And in addition, there are mysteries of the radiation, the way solar energy is absorbed and deposited in the clouds and in the atmosphere, that we would really like to understand, both to understand Venus and also just to round out our understanding of the way climate works on planets, which of course is very important to us here on Earth, struggling with climate change. There are measurements we would love to do within the atmosphere of Venus that could tell us more about the origins and evolution of that planet.
The tough balloons will last for many months. Their sensors alert for low-frequency infrasonic waves.
Is Venus volcanically active? Does Venus have plate recycling today? Those are geophysics questions that can be answered through seismology, which we can do from balloon, potentially, by measuring, this is wonderful, taking advantage of the fact that the Venus atmosphere is so thick that sound waves from earthquakes will propagate up through the atmosphere and can be measured from balloon or from orbit. It's astounding.
Each science buoy makes a trip around the globe in about 4 Earth days. As they spread out, they form a global network, performing standoff seismology, meteorology, atmospheric chemistry, and surface observations. But if these balloon probes can collect all these data, why send people all the way to Venus?
Humans can do things that robots can never do. That's just a fact. We can think on the fly. We have hands. The difficulty of putting hands on another planet is just, it's extraordinary. And link them to a mind. So we could, with humans in the Venus clouds or in orbit at Venus, make observations. It would be telescopic observations, measurements of chemistry, or set up an observatory at Venus to study the Venus clouds and changes that we might expect to be coming from volcanic and seismic activity at Venus. So it's the Lando Calrissian model, right? the cloud society at Venus. We would get more data by having people there.
Human beings are marvelously versatile, but human explorers are a lot harder to keep alive in the atmosphere of Venus. They need oxygen, they need food, they need sleep. So I'd love to see human explorers go to the atmosphere of Venus. I'd love to see human explorers that could operate via telerobotics some of our high temperature systems on the surface of Venus, so that the humans would be in the atmosphere, but they're controlling by virtual reality a system that's on the surface of Venus. That would be a pretty advanced mission. It's not something that we're quite ready to do quite yet.
Success of such missions will depend on the people who fly them. No matter how comfortable the cloud community dwellings, scientists and engineers may only agree to work there if there's a guarantee of return to Earth. Habitats in the clouds require energy. One way to get it is to troll for power. Extend a strong cable from the cold altitude of the dwelling down into the hot depths of the atmosphere. But don't let it touch the ground. The difference in temperature between the cable's top and bottom can generate electricity, employing what's known as the Seebeck effect. It's an electro-thermodynamic device that needs no moving parts. But there may be an even simpler solution, one that puts no drag on the floating station.
As you get higher and higher, as you get above the thickest of the cloud decks at about 50 kilometers above the surface, once you get above the cloud decks, it gets very sunny. It's actually sunnier than the Earth. It's not ferociously hot because there's still some amount of the high cloud that diffuses the light a little bit, but there's plenty of solar energy. So I picture the habitats that could float in the area above the thick clouds of Venus probably as being solar powered. There's plenty of sunlight, the temperature is nice. Why not pop out your solar panels and run on the sun? It should work.
Solar power on Earth depends on batteries to store the energy after sunset. But nighttime on Venus is much longer.
The surface of Venus rotates very slow and backwards. So if you were on the surface, the day-night cycle would be hundreds of days. But once you get above the surface, what happens is the clouds whip around the planet very quickly. So there's a phenomenon called atmospheric superrotation. That means that the atmosphere actually rotates faster than the planet. So at the Earth-like level, at about 50 to 60 kilometers, it takes about 4 days for the winds to circle the planet. So if you were floating in a balloon or in a habitat that was just stationary and following the winds, you'd see about 2 Earth days of sunlight, and then you'd have about 2 Earth days of nighttime. So when you're talking about power for the habitat, of course, you would have to provide for power for the nighttime. Your nighttime's going to be about 2 Earth days, but that's not impossible. You could imagine being solar powered during the day and then having enough energy storage to keep on living and working and doing whatever you're doing for your human habitats during the nighttime.
Like the International Space Station, a modest-sized floating field station could support a small group of researchers for deployments lasting several months. But using these same materials and construction techniques, there's practically no limit to how big these structures could be built. Many could cluster together to support a relatively large group of astronauts over much longer periods.
I picture the idea of these habitats as being the size of cities, kilometers in scale. So I sort of love the idea. And of course, once you put in one city in the atmosphere of Venus, why not more? Why not 10? Why not 100? Why not 10,000? There's a lot of Venus out there.
But how safe are these structures?
Well, the nice thing about the balloons in the atmosphere of Venus, if they're very, very large, is that they'd be running with the inside pressure about the same as the outside pressure. So it wouldn't be like a space habitat, say an O'Neill habitat in Earth orbit, where if you puncture a hole in it, you get an explosive decompression and all of the air rushes out. You'd have, well, the outside air is about the same pressure as the inside air. There'd be some exchange of gases. You wouldn't want that, but it wouldn't burst like a balloon in a catastrophic failure. When you have something this big, it takes a very, very long time to decompress. If you pop a balloon that's this big, it's over in an instant. But when you put a hole in a balloon that's hundreds of meters across, it takes a long time to deflate. And something that's thousands of meters across a city would take days and days to lose very much atmosphere. Nevertheless, of course, I think you'd want to work very hard to make sure that you don't get those punctures. And you'd make sure that you have multiple lifting gas areas so that even if you did, for one reason or another, have a failure that made one part of the city lose atmosphere, well, the rest of it would have enough lifting gas to hold you up.
These are large, complex assemblies. Fortunately, very little of their mass would have to be hauled here from Earth.
A lot of the materials that you could use to build a habitat, you might be able to make just from the atmosphere of Venus. It turns out that in modern engineering, one of the most versatile, one of the most useful materials you can make is carbon fiber. Carbon fiber is strong, it's lightweight. You can do a lot with carbon fiber. But of course, to make a whole city, you need more than just the structural members of carbon fiber. So I expect that if we were making a city, or 10 cities, or 1,000 cities, we're probably going to have to go down to the surface and grab up materials. So you will be mining the surface of Venus to bring up other materials, like the silicon and the silicate rocks and the lesser materials. There's a lot you can get out of the atmosphere, but not everything, of course. What you want to avoid doing as much as possible is you want to try to avoid bringing things all the way from Earth. Because the key to living in the solar system is learning to use the materials that you can find on hand. Bringing things up from Earth is a camping trip, but we don't want to just go camping. We want to live in the solar system.
What began with a few science outposts and airships could expand into a far-flung, interconnected network of communities beyond Earth. The old romantic vision of self-sustaining space settlements could come alive in the orbit of Venus. Habitats many kilometers in size can be constructed from materials mined from the atmosphere or asteroids, and they'd be powered by free energy from the nearby sun. These utopian structures could rotate to provide comfortable gravity and pleasant weather. Large ships could dock there, bringing cargo to be distributed down the gravity well to the floating towns in Venus's atmosphere. But the builders of such a city will have to wrestle with one inevitable design constraint. Most of the mass must be allocated to sheltering the residents from radiation.
If we had a colony at the Lagrange points, for example, we'd probably have to shield them with many meters of regolith, of dirt. Well, that's okay. We can mine dirt from the moon. The moon's got plenty of dirt. But that's a lot of stuff you have to bring for no other purpose than hiding away from the particles coming away from the sun, from galactic cosmic rays coming in from outer space.
On the other hand, the cloud dwellers would be safely tucked into the atmosphere.
Venus does not have a magnetic field to deflect particles, but it still does have an atmosphere. So at the level of the middle cloud deck of Venus and a little bit above, we're still talking about a lot of atmosphere between you and space. So the good thing is that we have enough atmosphere to attenuate the worst of the radiation. We're not getting the protons from the solar flare coronal mass ejections that would be very, very dangerous, maybe very deadly for an unprotected human. We get the 10 tons of atmosphere per square meter shielding us from the radiation. Another reason that the clouds of Venus are a nice place to colonize.
Venus has nearly the same gravity as Earth. While it has much more land area, it has no oceans. What would it take to make the entire planet livable? To terraform it? We would have to re-water the whole world. In the early solar system, the second planet, Venus, may have been the most hospitable of all. But as the sun brightened, Venus struggled to hold on to its oceans. Carbon dioxide and methane from volcanoes trapped heat, evaporating the seas. Atmospheric water vapor became a greenhouse gas, holding even more energy from the sun and the planet below.
4.5 billion years ago, Earth's atmosphere was also CO2 rich. That is the original atmosphere of the terrestrial planets. Venus has a very thick carbon dioxide atmosphere today, and we would too if you took all of the carbonate rocks, the rocks that hold carbon, took all the limestone on Earth, took Florida, evaporated it back into the sky, all that carbon dioxide would be about the equivalent of the carbon dioxide that's in the Venus atmosphere right now.
Venus is really off the scale in a sense. For us to load our atmosphere with the amount of CO2 that's in Venus's atmosphere would require us to free up all the carbonate rocks on our world and get all that carbon into the atmosphere. And that would take hundreds and hundreds of millions of years.
Space visionaries today are looking to advanced technologies to send Venus back in a more Earth-like direction.
You would have to obviously do something about the very, very strong greenhouse effect. Maybe you would do that by putting aerosols into the atmosphere, filling the atmosphere with dust long enough to collapse that greenhouse and get that CO2 to condense out on the surface. And then you'd have to find some way to keep it condensed out, maybe with, now we're getting science fictional here, but maybe with orbiting mirrors or something to cut down on that solar radiation.
British scientist Paul Birch proposed transporting trillions of tons of hydrogen from gas planets such as Jupiter. The idea is to convert atmospheric CO2 into oceans of water, plus mountains of graphite. Birch also suggested shielding Venus from the sun's heat with enormous thin panels to cool the atmosphere, shrink its volume, and lower its pressure. These giant screens would convert solar energy to power other terraforming operations, like capturing carbon and sealing it underground. Nobel Prize winner Paul Crutzen proposed injecting sulfur dioxide into the air to simulate the dark smoke of gargantuan volcanoes to cool the surface and tame the greenhouse. David Grinspoon and Mark Bullock suggest that exposing native calcium and magnesium could pull carbon down into carbonate rocks. But where to find a whole planet's worth of water?
Fortunately, I suppose, if this was your goal, there's a lot of stray icy objects in the solar system. The whole outer solar system, the Kuiper Belt, is loaded with icy objects, and would not miss a few of them. There are literally trillions of icy objects out there. So if you're imagining some far future where somebody's got the technical prowess and the will to do this, I would take some of these large icy objects, some large number of them, and crash them into Venus, which would both raise the dust to collapse the greenhouse and would return Venus to a more watery condition. This is not a near-term project.
To put icy objects on a collision course with Venus takes delicate orbital mechanics, a slow-motion ballet of many small robots with the collective power to move mega mountains. The swarm distributes itself according to the unique gravity map of the chosen object. Choreographed clusters of thruster firings nudge each massive ice world inbound onto its own safe trajectory. The bots may process their captured objects, separating out water and extracting metals during their long journey to the inner solar system. The icy bodies may change shape as materials are mined. These intelligent machines might also make clones of themselves to scale up the operation and get it done faster. When the processed icy asteroids arrive, they'll be delicately maneuvered into impact speeds that preserve the most water. Dust from the crashes should cut down sunlight, cooling it quicker. But smack the planet too hard, and you may unleash hell. Count on Venus to fight back. With a thicker crust and no plate tectonics, Venus doesn't vent its internal heat as easily as Earth. It builds up. This world has erupted and repaved its entire surface at least once in its history. To remodel an entire planet seems like the ultimate act of hubris. But we're already doing it.
Could we ever terraform Venus and go live on it? Well, you know, our more immediate task is to avoid Venera-forming Earth right now. That is, to not turn Earth into Venus by increasing the greenhouse effect. So I don't advocate immediately going and trying to live on Venus or Mars and trying to terraform them to, you know, escape from our problems here. However, the mental exercise of imagining how we would terraform another planet, I think, is very valuable for our task of learning how to manage ourselves on Earth better. Because it forces us to ask, how would we interact constructively with the planet? How would we intentionally alter a planet's climate and manage a planet's climate, as opposed to unintentionally and inadvertently messing with a planet's climate as we've been doing here on Earth?
I think actually learning to live in the solar system is going to teach us ways to help us live on Earth. What we call pollution on the Earth. On the Moon, we'd call that valuable resources. That's going to help us live on Earth. Just understanding that an ecosystem is a closed cycle. There is no such thing as waste. All of the waste has to be recycled and come back.
On the other hand, learning the techniques to better manage Earth might just give us the tools to tackle living on or around other worlds. It might take decades, centuries, millennia. But our distant descendants may well be born into a solar system with more than one place to call home. Some may be in the clouds of atmospheres. Some may orbit freely. Still others might live on the surfaces of worlds.
I think we should move out into the solar system, and I really want to go everywhere. I want to put human beings at the poles of Mercury. I want to go to Venus. I want to go to Mars. I think we should go into the outer solar system and start looking at some of the resources of the Kuiper Belt. I think human beings can, and we should, settle the whole solar system.
As it was when the planets first formed, Earth's twin may beckon us to its shores.